Earlier, you learned about the rectilinear motion of bodies. In simple terms, rectilinear motion is a motion that occurs in a straight line. The motion of a body in a straight line is treated as one-dimensional motion. The description of motion of a body involves its position, displacement, velocity, acceleration, and time. In the one-dimensional or straight-line motion of a body, you are able to represent all these entities on a number line. A number line has an origin, and measurements to the right of the origin are taken as positive and to the left taken as negative. By adopting a proper sign convention for all the entities, you are able to solve the problems analytically. Before you proceed to the next topic that deals with two-dimensional motion of a body, that is, motion in a plane, you need to evolve a new way to represent these entities, as the number line method will not adequately describe and represent them. To fulfill this need, a new way called vector representation is used. Before learning this, you need to learn the basics of scalars and vectors. Let us start with scalars. Entities described completely with the help of a number, along with its unit, are called scalars. The mass of an object is 10 kg. This description is complete, and you do not need to add to it to identify it. Similarly, the distance between point A and point B is 20 centimeter, is a complete description. Likewise, the temperature of a body and the time at which an event takes place are described completely by a number along with corresponding units. A number along with a unit that represents the measure of a physical quantity is called its magnitude. Thus, mass, distance, and temperature are scalars. As with numbers in elementary mathematics, scalars can be added, subtracted, multiplied, and divided. Operations on scalars are the same as in elementary mathematics and algebra, whereas operations on vectors obey the triangle law and parallelogram law of addition. You will learn various operations on vectors one by one in detail. First, let's start with multiplication of a vector with a real number. When you multiply a vector p with a positive number, lambda, you get a vector whose magnitude is changed by the factor lambda. The direction remains the same as that of p. Mathematically, it is expressed as mod of lambda p is equal to lambda into mod p. For example, when p is multiplied by 4, the resultant vector is 4p, whose magnitude is 4 times that of mod p. On the other hand, when you multiply a vector p with a negative number, lambda, you get vector minus lambda p, whose direction is opposite to the direction of p, and its magnitude is minus lambda times that of mod p. For example, when you multiply p with minus 3, you will get vector minus 3p, whose magnitude is 3 times mod p and direction opposite to the direction of p. The dimensions of lambda p is the product of the dimensions of lambda and p. Next, you will learn about addition of vectors by the graphical method. In the graphical method of vector addition, either the triangle law of addition or the parallelogram law of addition is used. Now let us add two vectors by the triangle law of addition. Consider two vectors P and Q lying in one plane. Draw a line AB parallel to P. The length of AB is equal to the length of P. Display an arrowhead at B. A is known as the tail of P and B is known as the head of P. Then draw a line BC parallel to Q and equal in length to Q. Display an arrowhead at C. B is the tail of Q and C is the head of Q. Note that the tail of the second vector always coincides with the head of the first vector. Now join AC. Display an arrowhead at C on line AC. AC is vector R, obtained by adding P and Q. Similarly, draw a line DE parallel to Q. The length of the line DE is equal to the length of Q. Display an arrowhead at E. Then draw line EF parallel to P and equal to the length of P. Put an arrowhead at F. The tail of P coincides with the head of Q. Now join DF. Display an arrowhead at F on the line DF. DF is vector R obtained by adding Q and P. Here, vector R obtained by adding P and Q is the same as obtained by adding Q and P. This vector addition is the commutative property of vectors. Vectors also obey the associative law of addition. To understand this, consider three vectors A, B and C lying in one plane. Add A and B to get D. Then add D and C to get R, which is the final result. Similarly, add B and C to get E. Then add A and E to get R, which is the final result. Here, A plus B plus C is equal to R in every case. This proves that vectors obey the associative law of addition. What happens when you add two vectors that are equal in magnitude but opposite in direction? It results in a vector possessing zero magnitude and is called a null vector or a zero vector. In case of a null vector, you cannot specify direction. Various operations with a null vector are A plus 0 is equal to A. Lambda 0 is equal to 0. And 0A is equal to 0. Let's discuss the physical meaning of a null vector. Consider a body is occupying position P with its position vector R at time t. From time t to t dash, It moves from position P to P dash. Its position vector at time t dash is r dash. From time t dash to t double dash, it moves back from position P dash to P. The displacement of the body during the time interval t to t double dash is 0, as the body has returned to its initial position. Its displacement is thus represented by a null vector, which is just a point with 0 magnitude and without any arrow. Now let us discuss the parallelogram method for the addition of vectors. Consider vectors A and B, which are to be added. Redraw the two vectors with their tails coinciding at a common origin O. Complete the parallelogram by drawing parallel lines. Then, draw a diagonal passing through O. At the end of this diagonal, display an arrowhead. The diagonal represents the resultant vector R. After addition, you will now learn about the subtraction of vectors. Direct subtraction of vectors is a little confusing. To avoid this confusion, you must use the concept of addition of vectors after reversing the direction of the second vector. Vector minus B is added to vector A to get R. This method makes the subtraction of vectors easy. Earlier, you learnt about the addition of vectors by the graphical method. The accuracy of the results obtained using the graphical method depends on the scale you chose and your ability to draw exact parallel lines. You can get accurate results using the analytical method of vector algebra. Before learning the analytical method of vector algebra, you should understand the concept of resolution of a given vector in any two required directions. To understand the resolution of vectors, consider three vectors A, B, and C lying in one plane. In this case, you need to resolve vector A along the directions of B and C. O and P are the tail and head of A respectively. From O, draw a line parallel to B, and from P, draw a line parallel to C. Let these two parallel lines intersect at Q. On the line OQ, display an arrowhead at Q. Similarly, on the line QP, display an arrowhead at P. In this case, the length of the line OQ is 2.5 times the length of B, and the length of the line QP is 3.2 times C. Hence, from the triangle OPQ, you can write A is equal to 2.5 times B plus 3.2 times C. 2.5B and 3.2C are known as the components or resolved parts of A along the directions of B and C. In this expression, B and C are the unit vectors, and 2.5 and 3.2 are real numbers. Usually, vectors are resolved along the axis of a rectangular coordinate system using unit vectors for convenience. Unit vectors have a magnitude equal to unity, and they indicate a particular direction. You do not specify any dimension or unit for these vectors. They only indicate direction. Unit vectors along the direction of the x, y, and z-axis of the rectangular coordinate system are denoted by I cap, j cap, and k cap respectively. These three unit vectors are perpendicular to each other, as the three rectangular coordinate axes are perpendicular to each other. Now, let's see how vectors are added by the analytical method. First, we will discuss vector addition for planar motion or two-dimensional motion. When dealing with planar motion or two-dimensional motion, you need to resolve the given vector along I and j only. Now, consider a vector A on the xy plane. From the head of the vector, draw perpendicular lines to the coordinate axis to obtain vectors A1 and A2. Hence, we can write A is equal to A1 plus A2. Let this be equation 1. As A1 is parallel to I, you can write A1 is equal to AXI. Let this be equation 2. Similarly, A2 is equal to AYJ. Let this be equation 3. Substituting 2 and 3 in 1, you get A is equal to AXI plus AYJ. AX and AY are the magnitudes of the components of A in the x and y direction. Here, A makes an angle theta with the x-axis. You can write AX is equal to A cos theta and AY is equal to A sin theta. Let these expressions be equations 4 and 5 respectively. AX and AY can be positive, negative or 0 depending on the angle theta. A can be specified by its magnitude and theta, or its two components AX and AY. When A and theta are given, AX and AY can be determined using equations 4 and 5. When AX and AY are given, you can find A and theta as shown here. Now, let us solve a simple problem to understand the procedure associated with this method. Two vectors A is equal to 7i plus 3j and B is equal to 5i plus 8j are given. You are asked to add these two vectors and find the resultant vector C. To understand the procedure clearly, you need to first solve the problem using graph paper. To draw vector A, first mark the point 7, 3 on the graph paper. 7 is a coefficient of I and 3 is the coefficient of j. Join this point with O with a straight line. Draw an arrowhead at the end of this line. This line with the arrowhead represents vector A. Similarly, represent vector B by joining the origin O to point 5, 8. Complete the parallelogram by drawing parallel lines from the arrowheads. Draw the diagonal passing through O. Display an arrowhead at the end of this diagonal. This diagonal represents the required resultant vector C. Check the coordinates of the arrowhead point of C, which should be 12, 11. You can also solve this problem without graph paper. You need to simply add the coefficients of I and j as shown here. However, representing the given vectors on graph paper helps you visualize the procedure. Now, let's discuss vectors in three-dimensional space. Create x, y, and z coordinate axis passing through point O. Then represent a vector A passing through O. Here, alpha is the angle between vector A and the x-axis. Beta is the angle between vector A and the y-axis. And gamma is the angle between vector A and the z-axis. In this case, its three components along x, y, and z direction can be written as ax is equal to a cos alpha, ay is equal to a cos beta, and az is equal to a cos gamma. Here, a is equal to ax plus ay plus az, which can be written as axi plus ayj plus azk. Here, ax, ay, and az are scalars, and I, j, and k are unit vectors. The magnitude of A can be written as the square root of ax square plus ay square plus az square. Let us solve a simple problem using isometric graph paper. Two vectors, A is equal to 6i plus 4j plus 9k, and B is equal to 4i plus 3j plus 2k, are to be added to find vector R. To visualize the process, you can represent A on the graph paper by joining the point 6, 4, 9 to the origin O. Similarly, join 4, 3, 2 to the origin O to obtain B. You can draw the resultant vector R after determining the coefficients of I, j, and k by simply adding the corresponding coefficients of A and B. Thus, you have learned the analytical method of vector addition for two-dimensional motion and in three-dimensional space. Earlier, you learned the addition of vectors by the analytical method using the triangle law. Now, you will learn the addition of vectors using the parallelogram law. Consider two vectors, A and B, passing through a point O. The angle between them is theta. To find the resultant C of these two vectors, complete the parallelogram with A and B as adjacent sides. The diagonal drawn from O of the parallelogram represents the resultant C of the two given vectors, A and B. The resultant vector C makes an angle alpha with vector A. In this figure, OP represents vector B. OR represents vector A. and OQ represents the resultant vector C. Extend line OR. From Q, draw a perpendicular to the extended line OR to meet at S. From R, draw a perpendicular to OQ to meet at T. The resultant vector C makes an angle beta with vector B. Consider the triangle OSQ. From the triangle OSQ, we can write OQ square is equal to OS square plus SQ square. Let this be equation 1. As point R lies on the straight line OS, we can write OS is equal to OR plus RS and OS is equal to A plus RS. Let this be equation 2. Consider the next triangle QRS. From triangle QRS, we can write cos theta is equal to RS by RQ, which is equal to RS by B. By cross multiplying, we can write RS is equal to B cos theta. Let this be equation 3. From the same triangle QRS, we can write sin theta is equal to QS by RQ, which is equal to QS by B. By cross multiplying, we get QS is equal to B sin theta. Let this be equation 4. Substitute equation 3 into. We get OS is equal to A plus B cos theta. Let this be equation 5. Substitute equations 4 and 5 in 1. We get OQ square is equal to A plus B cos theta the whole square plus B sin theta the whole square is equal to A square plus B cos theta the whole square plus 2AB cos theta plus B sin theta the whole square is equal to A square plus B square sin square theta plus cos square theta plus 2AB cos theta. C square is equal to A square plus B square plus 2AB cos theta. C is equal to square root of A square plus B square plus 2AB cos theta. Let this be equation 6. This equation is known as the law of cosines. Using this, we can find the magnitude of the resultant vector. Now, consider the triangle OSQ. From triangle OSQ, we can write sin alpha is equal to QS by OQ. QS is equal to OQ sin alpha. QS is equal to C sin alpha. Let this be equation 7. Consider the next triangle RSQ. From triangle RSQ, we can write sin theta is equal to QS by QR, which is equal to QS by B. QS is equal to B sin theta. Let this be equation 8. Equating 7 and 8, we get C sin alpha is equal to B sin theta. C by sin theta is equal to B by sin alpha. Let this be equation 9. Now consider the next triangle ORT. From triangle ORT, we can write sin alpha is equal to TR by OR is equal to TR by A. TR is equal to A sin alpha. Let this be equation 10. Consider the next triangle QRT. From triangle QRT, we can write sin beta is equal to TR by QR, which is equal to TR by B. TR is equal to B sin beta. Let this be equation 11. Equating 10 and 11, A sin alpha is equal to B sin beta. A by sin beta is equal to B by sin alpha. Let this be equation 12. From equations 9 and 12, we can write A by sin beta is equal to B by sin alpha is equal to C by sin theta. Let this be equation 13. Now consider triangle OQR. Here, A by sin beta is equal to B by sin alpha is equal to C by sin 180 minus theta. A by sin beta is equal to B by sin alpha is equal to C by sin gamma. Let this be equation 14. This equation is known as the law of sines. From equation 14, we can write sin alpha is equal to B by C into sin gamma, which is equal to B by C into sin 180 minus theta. And finally, we can write sin alpha is equal to B by C into sin theta. Let this be equation 15. From this equation, we can find the direction of the resultant vector C. Consider the triangle OQS. From triangle OQS, we can write tan alpha is equal to QS by OS is equal to QS by OR plus RS. Tan alpha is equal to B sin theta by A plus B cos theta. Let this be equation 16. From this equation 2, we can find the direction of the resultant vector C. Thus, the parallelogram law helps you find the magnitude and direction of the resultant vector C. C is equal to square root of A square plus B square plus 2AB cos theta. This equation is known as the law of cosines. Using this, we can find the magnitude of the resultant vector. A by sin beta is equal to B by sin alpha is equal to C by sin gamma. This equation is known as the law of sines. Sin alpha is equal to B by C into sin theta. From this equation, we can find the direction of the resultant vector C. Tan alpha is equal to B sin theta by A plus B cos theta. From this equation too, we can find the direction of the resultant vector C.